If you're cramming for your board exams, you know solutions is a massive chapter. But what if I told you we could nail down all the core concepts in just the next 5 minutes? Well, that's exactly what we're about to do. All right, let's dive right in.
So, think about this for a sec. You've got solid metal alloys, a gas like humid air, and of course, the sugar water you might have had this morning. What on earth do these three things have in common? Well, they are all perfect examples of solutions, and that's what we're tackling today.
First things first, let's break down what a solution actually is. Every single one, no matter how simple or complex, is really just made of two key players.
So a solution is what scientists call a homogeneous mixture. Now, that's just a fancy way of saying it's mixed so perfectly and evenly that you can't see the individual bits. For your exams, you're almost always going to see binary solutions, which just keeps things simple. It means a mixture of only two components.
And those two components, they're the solute and the solvent. The rule of thumb is super simple. The solute is the thing you have less of, and the solvent is the thing you have more of. Just picture a little bit of sugar, that's your solute, dissolving into a whole glass of water, your solvent.
But what about a trick question where the amounts are exactly equal? Here's a pro tip for you. You just compare the number of moles. A mole is just a way of counting the actual number of molecules. So the substance with more molecules, more moles, that's always the solvent. Don't forget that one.
Okay, so now that we know our players, the solute and the solvent, let's see all the different combinations we can make. When you mix and match the three states of matter, solid, liquid, and gas, you can actually create 9 totally distinct types of solutions.
And they're pretty cool. You can have a gas dissolved in a liquid, which is just the CO2 that makes your soda fizzy, or a liquid in a liquid, like ethanol in water. You can even have a solid dissolved in another solid. That's literally what a metal alloy is. The possibilities are everywhere.
Knowing the types of solutions is one thing, but as a chemist, you always have to ask, okay, but how much solute is actually in there? That's where we get into the idea of concentration.
Now listen up, because here is a classic exam question that trips students up all the time. When we're measuring concentration, which of those measurements is going to change if the temperature goes up or down?
And here's the secret, it's actually really simple. Anything that's based on volume is temperature dependent. Why? Because volume expands and contracts with heat. But anything based on mass is temperature independent, because an object's mass doesn't change. This distinction is absolutely huge for your exams.
First up, we have molarity with an R. This measures the moles of solute per liter of the entire solution. See that word, liter? That's a unit of volume, which means if you heat the solution up, the volume expands and the molarity will change.
Then we have nolality, with an L. And you have to pay attention here, because the details are critical. It's the moles of solute per kilogram of just the solvent. See the two huge changes? We're using mass, kilograms, instead of volume, and we're only looking at the solvent, not the whole solution. Since mass doesn't change with heat, molality is temperature independent.
So, we can measure solutions, but what actually controls the process of dissolving in the first place? Well, that brings us to our final topic, solubility.
Solubility is basically the limit. It's the absolute max amount of a solute you can possibly dissolve in a solvent at a specific temperature. Kind of like a sponge that's completely full of water, it can't hold anymore. Once you hit that limit, we call it a saturated solution.
And the golden rule that governs all of this is beautifully simple. Like dissolves like. This just means that polar things, like salt with its positive and negative charges, dissolve really well in other polar things, like water. And nonpolar stuff dissolves in other nonpolar stuff. Easy, right?
You know, from experience, we all know that heating up water helps sugar dissolve in our tea. But is that always true? Does cranking up the temperature always make things dissolve more easily? Well, the answer depends on whether the dissolving process is endothermic or exothermic. Endothermic processes like sugar and water actually absorb heat from their surroundings, they feel cold. But exothermic processes like quicklime and water release heat, they get warm. To understand this whole relationship, you only need to remember 2 little words. This is the key, you ready? Exo, inverse. Just burn that into your brain.
The exo-inverse rule is a game changer. It means that for exothermic reactions, the relationship between temperature and solubility is inverse. As you increase the temperature, the solubility actually goes down. For endothermic reactions, it's direct. More heat means more solubility, just like with our sugar example.
Okay, time to apply our new rule. What about dissolving a gas into a liquid? You know, like the oxygen that fish need to breathe in the water. How does temperature affect that process?
Well, here's the one fact you need to know. Dissolving any gas into a liquid is always an exothermic process, every single time, no exceptions. So what does our exo-inverse rule tell us is going to happen?
Well, if dissolving a gas is exothermic, our exo-inverse rule means that colder water holds more dissolved gas, including oxygen. And that leads to a final big picture thought. Where in the world's oceans, the warm tropics or the freezing cold poles, would you expect to find the most abundant life? It's a question that connects one simple chemistry rule to the entire global ecosystem.